Hello, my name's Chris. I'm a senior lecturer in control systems engineering here at Loughborough University. I teach primarily on the electrical programme, so electrical electronic engineering, ECS and the RMCE course. It's at this point that I normally ask people, well, what is control engineering? Do you understand what it is? And it's never desperately easy to answer, which is why I've got some very sophisticated props here with me today. And I guess most of us have had a go at this, balancing a stick on your hand in the garden. And believe it or not, this is a control system. This is a mechanically unstable system. If I let go, it would fall over. It's something called non-minimum phase. So actually, I need to put a control action in the wrong direction. But what I'm doing is moving the ground plane to stabilize this stick, essentially. And yes, that's balancing a stick. But if we relate that back to human beings, we're full of control systems. If you think about this stick or this inverted pendulum, I'm exactly the same, stood up right now. I've got a point on the ground, and I'm basically this inverted pendulum. Now, to control this system, I've got something on the top of my head. It's called a brain, which is a fantastic computer, and that's making decisions all the time. I've got sensors, which are my eyes, so I can see where I'm oriented, and I've also got actuators, so muscles pull against tendons, pull against my skeletal structure. And that works in a continuous, what's known as closed loop. So I use the sensors to work out where I am oriented. My brain then works out from those signals what signals to send down to my actuators, and that keeps me upright. And we know we can disturb this closed loop because if we carry something that's too heavy, we've fundamentally changed the system. Or if you've ever gone to the pub on a Friday or a Saturday night and had too many beers, you know that you can stumble around and you've disrupted that control system. So there's loads of examples of control systems in nature, but there's also loads of control systems inside everything that we interact with. So I brought along another expensive prop today. This is a little model of a Spitfire. But essentially aeroplanes like this are naturally stabilizing. So they have a centre of pressure, so where the lift acts, which tends to be behind the centre of mass, and so they have a self-restoring force. But modern fighter jets and modern airliners don't work like that. They have a centre of pressure which is in front of the centre of mass. So if they fly along normally, they want to essentially flip on their backs. But the reason for that is that you get fabulous turn performance. Fighter jets, you want to be able to turn inside the other aeroplane. So if you've got an unstable system, it wants to turn really, really fast. We make that work by having lots of computers on board the aeroplane, lots of sensors like gyroscopes, and we close that loop. So when the pilot pulls the stick back, they're not really in control. They're putting a demand for how fast the aeroplane wants to turn, and the aeroplane then determines that and uses the actuators to move the surfaces to be able to enable that. What we teach here, or what I teach particularly, is control systems, and it's exactly that kind of process where we're looking at taking mechanical systems generally, can be electrical systems, using sensors, actuators, and some computation to get that system to work. Now, it's difficult to get things like Eurofighters, F-35s, even Spitfires into a lab, so we condense that down into something that's much simpler, which is what I'm going to show you here today. Okay, so what we have here is a fundamental part of our second year control course, where we essentially introduce the basics of control engineering. The first thing you need to understand is how to model the physics of a system, so we'll take you through that principle. You then need to be able to analyze a system, so we show you how to do things in the time domain, and something that always confuses people is the frequency domain. And then from that, we show you how to design controllers. And a lot of that is delivered in the lecture theatre environment, but we always marry that back to something we can do in a laboratory environment. So that's what we have here, because that really makes the concepts come alive. This here is quite a simple system, but it's a very effective way to show you what's going on. At the bottom here, we have a DC motor. Okay, you put a voltage in, the thing spins. And we've got a flywheel on the top. So that's our system dynamics. And we go through how to model this, how to understand the physics of what's going on. We've got a big brain here. So this is what's known as a National Instruments MyRio board. It's got lots of inputs, lots of output channels. And what we can do through the computer here is put a program on there to tell this system what to do. The final thing is that we've got some sensing at the bottom. So we've got an angle encoder here, so we know exactly where that motor is. So this is our feedback signal, this is our brain, and this is our system here. So what you do is you come into the lab, we do an experiment where you can characterize this system, see if it matches against the reality. We then get you to design some controllers, and that's essentially what you can see here. We can put a demand signal in for the speed of rotation. That gets measured. We have an error signal from here. The MyRIO then works out how much voltage to put in the system, and what you should see is the yellow signal, which is the measurement, starts to match against the red. And we can play around with those control tunings to see if we can improve performance, see if we can get it closer to the demand signal. So those are the fundamentals that we teach in the second year. What I'll show you now is how we start to develop that, how it starts to get more complicated as we move on through the course. Okay, so we've talked about the basic principles in the second year. Then we start to build on these as the course progresses. And what we're showing here is the laboratory equipment that's associated with our third year course, where we start to develop more complex understanding of systems. So we start to model systems which are now multiple inputs and multiple outputs, use something called state space modeling for that, and there's associated control complexity that comes along with that as well. So again, we deliver a lot of this stuff in the lecture theatre environment to get you in this way of thinking and to understand what we're talking about. We then, again, drag you into the lab and we show you how to apply these techniques. So what we have here, again, is the same sort of setup. We've got a DC motor at the bottom. We've got a MyRIO again, so this is our brain. We've got the same sensor on the bottom of the motor, so we know where that's oriented. But we've now got a slightly more complicated system. We've got something called an inverted pendulum. And if you remember back to the beginning, it's exactly the same process. It's this balancing a stick like a human being, like the example in your garden with a broom, or something like a Eurofighter Typhoon. The way that we design controllers is exactly the same. So we get you to model the system, again, slightly more complicated, come and characterize that, see if the theory matches against what we've got here, and then get you to design controllers and choose these, what's known as state feedback gains, and hopefully this should work if I'm delicate enough. There we go. Okay, and as I said, that's exactly the same principle as the way that you design things with complicated aeroplanes. Okay, so you can see how through the degree program we start with some of the fundamentals in the second year for control. We develop into more complicated things in the third year. We then have further courses in the fourth year to take some of these ideas closer to how you would apply them in industry. But the other exciting thing for me, particularly as a supervisor, if you're interested in these concepts, is to apply them in a final year project where you get to build a system. You can get to test these concepts and really, really show how they work, and frankly, show off as well the skills that you'll have developed in your time here at Loughborough.